Hello, welcome to Aviation 101 with Laura. Back with this popular series about preparing for your aircraft dispatcher oral exam. And it's part 2 of my coverage of task D, weather-related hazards. So, if you haven't watched the other ones, go back and watch those because they've been getting a lot of positive feedback. I think that with studying, you will see that weather is so important for you to know as an aircraft dispatcher. So that, brings me to check out my other playlist. I have a playlist course that's all about weather theory. So if you are, watching this and just trying to check off, do I know how to answer these specific questions that she's asking? That's not enough. You actually need to really dive into weather theory and understand it. And hopefully your dispatch training program is providing that to you, or you have that from other means of study. The other thing I just want to say again is with the channel memberships, they have been taking off. I think I have 7 or 8 members, which is amazing. Thank you guys for supporting me. You know who you are. And, if you want to shout out, reach out to me and I will put your name on the video somehow or something. But I am excited about those. If you want to sign up, there's a link in the video description. And we are coming up eventually on the next Monday members only meetup. And that's a live stream where you can, just for members, and you can log in and ask questions. And then I release that content publicly later. But yeah, so on to this topic, task D. The last one I made in this series was with a specific flight scenario. This time I want to talk about some specific questions, just the theory behind these areas that the FAA has got in the FAA Aircraft Dispatcher Practical Test Standards. So without further ado, let's get started with talking about crosswinds and gusts. What are some conditions where you would expect there to be strong gusts as an aircraft dispatcher? Okay, well, sometimes when we expect gusty conditions would be where we have a cold front approaching or have gone through the area. Sometimes that brings gusty winds. So we have a immense quick change in pressure happening at a short period of time. We also can expect gusty winds if you have a strong surface wind, but then obstacles such as terrain or even buildings, hangars near the runway, and you end up with gusts and variable direction winds on takeoff or landing. You also, of course, have thunderstorm potential activity. We can cover thunderstorms in greater detail. Sometimes gusty winds are a result of a sea breeze or a land breeze where we have a cycle of air flowing either in from the sea or out from the land, depending on the time of day. This is common in more coastal areas. Okay, let's talk about crosswinds. Why are crosswinds potentially hazardous for aircraft operations? So crosswinds can be hazardous for aircraft operations. It requires the pilots to have more additional control inputs, to really be doing more corrections close to the ground. The aircraft is in a low energy, high drag state. If it's takeoff or landing, we have the landing gear extended. We have some flaps or slats extended depending on where we are at. And so we have the pilots in a busy environment, low to the ground, slower, and having to keep the aircraft on center line with changing winds, potentially with gust factors. But yes, the crosswind can pose some hazard to aircraft operations. Okay, so what is your aircraft's crosswind limitation? For the 737-300, the max crosswind component on a dry runway is 35 knots. Okay, you said the max crosswind component for a 737-300 on a dry runway is 35 knots. Why is it different on a wet runway? And what is it? Okay, on a wet runway, it is 15 knots. Why is that different? Well, okay, if a runway is wet or contaminated is, I guess what I should say, if it's anything besides dry, then it's 15 knots for the 737-300. The reason it's different is because the aircraft does not have the same amount of basically gripping strength of the tires, and we don't want to land with the aircraft going sideways and like so much control input that the aircraft then could be sliding off the runway. Okay, so a contaminated runway. How would you know that there was a contaminated runway at your destination? For the contaminated runway, I could tell that by looking at weather, especially for in real time. I would be able to look at a METAR and see if there was precipitation falling. I would assume the runway was wet. I can also kind of pre-plan contaminated runways if we look at the TAF and we can see that there's precipitation predicted during our arrival time, or even like plus or minus an hour. Just to be safe, I would want to plan that the runway could be contaminated. And yeah, so that's kind of how I would know. The other way to know is looking at NOTAMs. If I start seeing field condition reports, then I would know the runway was contaminated. And we already talked about field condition reports in a previous part of this oral, so if you want me to talk about that, I can. No, that's okay. You already talked about field condition reports. Okay, so let's talk about surface visibility restrictions. Why is that a concern for us in air carrier operations? Okay, well, when surface visibility is low, then we are going to be taking off or landing by the use of instruments. So we would need to basically allow for that. There are certain regulatory requirements where we cannot, for example, continue the approach. We actually cannot even begin the approach and go past the initial approach fix unless we have the visibility required to land. It's printed on the bottom of the chart. So I could not allow the flight to like continue. I mean, and the crew knows this, so they're not going to continue the approach if they're not allowed to begin the approach. They're not going to begin the approach. But you know, from a regulatory standpoint, if the visibility dropped after the initial approach fix, then they could continue. But it's on the crew to determine if they have the visibility needed to land the aircraft. As far as takeoff, I will be looking at the weather at the airport and determining I like to use the Jeppesen page where it shows our takeoff minimums, and we can use that to determine if we can allow the flight to be dispatched, because the visibility has to be above what's required for takeoff or the flight's not going to be going anywhere. Okay, what are some common restrictions to surface visibility? Some common restrictions to surface visibility are fog, mist, haze, smoke, precipitation, which there's a variety of types of precipitation, but if it's falling hard enough, or we have snow, even like freezing fog. So there's many things, even salt spray, like could be spray from water, can be a restriction to surface visibility. Okay, let's talk about turbulence. What causes turbulence? Okay, so turbulence is caused by a rapid change of wind speed or direction in a short area. I mean, basically, air is fluid, and so if it's moving and changing direction or changing speed in a small area and the aircraft flies through it, it can be affected by that movement of air, and that is basically turbulence. So what's wind shear then? Okay, well, again, the FAA defines wind shear as a sudden change of speed or direction of wind in a small area. And that could be like horizontal area or even like a vertical area. So when we have a sudden change of wind direction or speed, that's a potential wind shear situation. Of course, wind shear implies turbulence. And say, for example, we are coming in to take off or land, that really matters because now, again, I'm low to the ground, slow, lots of drag in the aircraft, like I mentioned before. And if we have a sudden change of wind speed or direction, the crew is going to have to compensate for that and change the airspeed accordingly. Okay. What is icing on aircraft and what causes that? Okay, so Aircraft icing is caused by the aircraft flying through an area where we have supercooled but still liquid water, and then the surface of the aircraft is below freezing. So really what happens is the aircraft flies through a cloud or precipitation that is still liquid. The cloud is made up of liquid, tiny droplets of water. If it's super cooled and the aircraft flies through there with a surface below freezing, those droplets get hit on the aircraft. When they get agitated, they essentially suddenly line all their ice crystals up and the thing freezes like instantly. So when we have an aircraft flying through an area with super cooled liquid water, but the temperature is below freezing in the air on the aircraft surface, that is where ice begins to be picked up on the aircraft potentially. It kind of depends on what part of the aircraft, depending on how the aircraft is designed. Okay, so when you're talking about icing, how would you even know as an aircraft dispatcher? Okay, well, as an aircraft dispatcher, I'm going to be looking at areas where there's clouds. We previously talked about satellite weather view. I can see there's clouds in satellite view, big picture. But I can also look at METARs to know where the ceiling is. I can look at TAF, so what's predicted. The METAR gives me the surface temperature, so that's nice, and the dew point, so I can tell if it's like below freezing at the surface. But I also can look at like the winds and temperatures aloft forecast. That shows me what the temperatures are aloft, and that way I can basically decide, well, if there's clouds that are aloft and the temperature is below freezing, and it's basically from about 0 Celsius to about -20 Celsius, but like there could be icing as low as -40. It's uncommon, but yeah, if we're down to like -20, we could be picking up ice even below that. And so then I know as an aircraft dispatcher. And there's other products such as like I can look at AirMets that would tell me about moderate icing. If it's severe icing, then a SIGMET would be issued, so I can look at that as well. So how does our aircraft avoid icing? Okay, well, the 737-300, when we talk about systems, we talk about the anti-icing systems, but we have a lot of protection against ice. We have heated areas of the wing leading edge. We have heated areas of the flight control areas. We have heating leaded edges on the tail surfaces. We have a heated windshield. We have various ways to know that ice is forming on the aircraft. We also have basically a heating area in the fuel to keep the fuel from getting slushy and frozen. This fuel doesn't like flowing if it's slushy and frozen. Yeah, and then, there's other aircraft have different types of ways to combat icing. The other thing is if you're taxiing and you're on the ground, you can't like run all your de-ice equipment. Then we have fluids that we can spray on the aircraft to remove ice. That would be a de-icing process. We have other fluids that can be sprayed on after de-icing to prevent more ice from forming, and that would be an anti-icing way to protect the aircraft, but there's various fluids applied in different ways. We can get into that if you want to. Now let's go on. Let's talk about thunderstorms. So thunderstorms, what are the stages of development of a thunderstorm? All right, so the thunderstorm begins with the cumulus phase. That's characterized by all updrafts, rising air. When the thunderstorm reaches the second stage, that's mature stage, then we have updrafts and downdrafts. We end up with precipitation falling within the thunderstorm, coming out of the bottom of the thunderstorm. And then the precipitation coming out, that signals the beginning of the mature stage of the thunderstorm. And then you have the dissipating stage of the thunderstorm. After approximately 20 to 30 minutes per thunderstorm cell, that's about how long they last. But after that period of time, the thunderstorm basically rains itself out, and it is characterized by predominantly downdrafts air just falling, and the thunderstorm eventually just dissipates. So those are the 3 stages. Okay, we talked before about, why thunderstorms are hazardous to aircraft, but, you mentioned before things about wind. How is that involved? What is like a microburst? I've heard of that related to thunderstorms. Okay, so a microburst is where we have a very small and intense downburst. As the thunderstorm reaches that mature phase, it can have a very small but very, very powerful downdraft of moving air as it basically falls down through the thunderstorm, carrying with it typically lots of rain, precipitation, comes out of the thunderstorm, and it's generally like less than a mile in diameter, this microburst, and also it lasts not that long, potentially 5 to 10 minutes, if that. But when it comes down, it is almost like you walked over to your kitchen sink, turned on the faucet full blast, the water comes out, it's going to hit the bottom of the sink and go splat and just go everywhere. Well, that's what happens with a microburst. If your aircraft is caught in that downward, basically rain shaft, falling air, it can be falling at 6,000 feet per minute. That's way too fast for an aircraft to outclimb it. So unfortunately, there have been some accidents caused by microbursts where an aircraft was flying through the area, it got into the microburst, and it did not apply power quick enough, or it just didn't have enough power to outclimb that downward air falling in the thunderstorm with the microburst, and it was crashed. There's been a few like that. Okay, so what do we do for this like wind shear worry and the microburst thing? What do crews do about that? Okay, well, for one, we shouldn't be flying through thunderstorms. The FAA suggests we give them at least 20 nautical miles berth. So we shouldn't be going near them. The crew has radar on board the aircraft to detect and avoid thunderstorms. They know how to use that radar, okay? Also, they have wind shear warning systems, like it's a predictive system that looks out ahead of the aircraft and basically evaluates if there's wind shear potentially up ahead, and it will give the crew an alert. So then they know, and they also practice these maneuvers in the simulator, like basically a wind shear recovery procedure. So they essentially know how to deal with this. But thankfully, since those predictive wind shear systems were deployed and more education was made available to pilots about microbursts, there have not been accidents with airlines involving these things for many years, thankfully. Okay, tornadoes. What's concerning about tornadoes? Okay, well, it feels like a silly question, but like a tornado is essentially a violently rotating whirlwind, and they can form on thunderstorms. It's actually still somewhat unclear to meteorologists why they form, but essentially, if you have a rotating column of air, which can come out of a thunderstorm, especially like a supercell or a severe thunderstorm, you sometimes see it as a roll cloud, but that would be like a horizontal area of tumbling air coming out of the front of a thunderstorm. If this somehow is basically coming down from the thunderstorm itself, again, it's common with the supercell type of thunderstorm, it's a tornado. A supercell thunderstorm is characterized by a lot of rotation. It's going to have a rotating updraft. And if that rotating updraft spawns a cloud coming out of the bottom of the thunderstorm, then that can form first a funnel cloud. If it touches the surface, then it's a tornado. So, that's basically what a tornado is. Okay, so how would you know if there was a tornado as a dispatcher? Well, as a dispatcher, I can obviously look at convective signets. Those are going to warn me of areas where there's convective activity predicted or happening. In a METAR, the code for a tornado is plus FC. If it is FC, that's funnel cloud. So I would know there. It's not common to see that in a METAR, but of course, if I saw that, I would definitely be passing it on to my crew. Okay, what is a hurricane and how do those form? Okay, so hurricanes are huge areas of low pressure. They tend to form in the US areas or in the Gulf and this part of the world anyway. They tend to form June, July, August, September, October, November. Very rare to have them in December. They form in areas of tropical disturbance off the coast of Africa. When the water is very warm, then they typically will move slowly as like a tropical depression area across the Atlantic, moving westward. As they go along, sometimes conditions favor them becoming up from a tropical depression, which is a low pressure, to a tropical storm, which basically is more wind and more low pressure. And once they reach a certain amount of wind speed, they get classified as a hurricane, which has a very low pressure in the middle. But it's basically a very large rotating low pressure. It has bands of thunderstorms that come out from this eye. The eye area actually is clear. Doesn't mean you should go flying through that, but these bands of weather come out from the thunderstorm and causes all kinds of hazards to people and aircraft operations, from bands of thunderstorms, which can spawn tornadoes, frequently do. We have storm surge, where basically the water rises suddenly up on the shore because it's basically coming up with this hurricane movement. Of course, very strong winds. We're talking about like 165 knots or greater if it's a very strong hurricane, and all the associated things with high winds. So yeah, hurricanes are typically the late summer, fall time of year in the United States. Okay, so what is the difference with the hurricane and a typhoon? Okay, so it's actually just where they're located. Like a hurricane is what they call them in the Atlantic, but then a typhoon would be something in parts of the Pacific Ocean. It's still a large, low pressure, organized storm system that is lasting for days, has movement. And it moves along, basically causing lots of chaos. Thankfully, we can see where they are with satellite. We have the National Hurricane Center that does a lot of predictions and evaluations. But yeah, that's a typhoon. It is really just a terminology difference. Okay, and lastly, volcanic ash. We talked about volcanic eruptions, how you would know they're happening, but why is volcanic ash a problem for aircraft operations? So volcanic ash is interesting. It's not really weather. It's of course a natural thing to happen. If we have a volcanic eruption, we do end up with something that looks like a cloud. The thing is, it's not a cloud like you would expect. It could have steam, of course, but also in this cloud of the volcanic eruption, we have basically particles of sand, ash. I don't know if I don't even want to call it sand, but it's like little rock particles that are getting spewed out of the volcano. So as they get spewed out of the volcano, they go very high in the atmosphere. I mean, we're talking about in the areas definitely where aircraft in air carrier operations are flying, like in the flight levels. So this cloud of ash, dust, rock, this not normal cloud, gets blown along, and it can linger for days, weeks. It can get blown through the jet stream. And if an aircraft flies through this area, the problem is when that material gets drawn into the aircraft jet engines, it actually tends to remelt, and then, because the engine is very hot inside, but then as it moves through the engine, it can solidify, and as it cools off, and then it actually forms basically like glass type of deposits inside the jet engine. This is very bad for the operation of the engine. And in fact, there have been a few instances where aircraft lost all of their engines because of ingestion of volcanic ash. Not just that though, we also have the issue of this smoke, ash, basically soot, tiny particles getting drawn into the cabin. They end up coming out of the cabin vents. It looks kind of like smoke, but it's a very fine powder that settles on everything. It's very bad. We don't want people breathing it. You also have the problem that since you're flying through basically a cloud of very fine particulate material, it sandblasts the aircraft, and it can sandblast windshields, windows, so it makes it impossible for the crew to see out of the aircraft when they actually come into land. So yeah, it's very bad. It's also hazardous to ground operations. It can settle on runways, taxiways, gets blown around, recirculated, sucked in engines that way. So all of this is very bad for aircraft operations. So how do you avoid this kind of thing? Okay, well, really it's, using these volcanic ash warnings, knowing where it's happening. I mentioned SIGMETs multiple times, but a SIGMET would be issued for a volcanic eruption. They provide predictions of where the ash cloud is happening so the aircraft can avoid it. Satellite views can help us avoid it, but it's not like something that the crew can detect on their onboard weather radar. And if it's night, again, this is why it's hazardous to aircraft, and how these aircraft accidentally flew in this area was night. There wasn't a good reporting system. They didn't know what they had flown into, and the engines just started flaming out. Now, granted, this was in the 80s, and we've gotten better at reporting and disseminating information about volcanic eruptions, but that's kind of a mini history about that. Okay, so covered a bunch of different weather-related hazards. Hopefully that's helpful to you guys. Next video, when it comes out, is going to be all about aircraft systems. I'm definitely going to be doing multiple videos about this because, yeah, commonly asked questions. And then eventually, yeah, there's so many areas on here. It just keeps going and going. So I don't know how many is going to be in that series, but stay tuned. Thank you for watching Aviation 101 with Laura. Don't forget to like, subscribe, consider being a channel member, comment, and share with your friends who would use this content, because I love growing the channel. Have a great day.